After launching SeqManEngine, click New Assembly to begin assembly setup. Select a variant analysis workflow. In this case, we're working with a human exome and using Illumina NGS data. There are many options for adding a reference. Here, I'll press the Download Genome Package button to download a human genome from the curated DNASTAR database. To add an optional bed file, I'll check this box and then browse to the file. My experiment is comparing 3 subjects, so I'll select multi-sample. Now it's time to add the data for the 3 family members. Since there's a separate data folder for each of these subjects, I'll use the Add Folder button 3 different times to add the data. None of these samples are controls, so I can skip to the next screen. To specify genders for the 3 family members, I'll click Set Experiment Genders. Since I'm working with human data, I definitely want to check the Variant Annotation database box. This ensures that the variants will be automatically annotated during assembly. This screen prompts me to enter a name for the project. This final screen shows how much disk space is required to run the assembly. This dataset is too large for my laptop to handle, so SeqManEngine recommends that I run the assembly on the cloud. To begin the assembly, I'll click the link and confirm my choice when prompted. At this point, SeqManEngine seamlessly uploads the data to the cloud and begins assembly. When assembly is complete, the results are then automatically downloaded to the local computer. When the assembly finished, I clicked a button in SeqManEngine to open the assembly results in ArrayStar, which you see here. The 3 experimental subjects are listed in the lower part of the screen. If I was to open the variance table at this point, we'd see a table showing thousands or tens of thousands of variants for each subject. I want to narrow down these thousands of variants to find only the variants that match a set of stringent criteria, which I'll go into in a moment. I can do that using the Advanced Filtering dialog. To start, I want to filter for variants that are present in at least one experimental subject, the daughter. To set up the filtering criteria, I'll then press Choose SNP Criteria. The first tab is the General tab. In this tab, I'll specify that the variants are heterozygous to the reference sequence and have non-synonymous translations. Now I'll move to the Statistics tab. In this Filter tab, I want to find variants that meet a 90% p-not-ref threshold and have a minimum depth of 20 sequences. Next, I'll move to the Population Genetics tab. In this tab, I'll specify that the variants should be minor alleles in the European superpopulation of the 1000 Genomes Project. The final tab I'll use is the Functional Prediction tab. Here, I'll specify that the variants are recorded as deleterious or damaging by LRT, Mutation Taster, and SIFT. Next, I'll start the search by pressing the Search button. 89 variants met all of the filtering criteria. The considerable reduction from the thousands of variants found originally. To view the variants in their own specialized table, I'll click the tool that looks like a table. In this table, you can choose from dozens of data columns using the Add Manage Columns tool. To save time, I've already chosen some columns of interest to this project. Let's look at the first row, which is a variant in the JMJD8 gene. You can see in the red columns that the daughter likely inherited this variant from her father. Clicking on any of the hyperlinks in this row lead to online references about the gene variant. For this example, I'll click the link to the Mastermind database. Mastermind found one journal article about this variant, and I can click on its link to see the PubMed synopsis. I can quickly see that the variant is associated with cleft palates.